this lecture. In this workshop, it's my great pleasure to introduce Jan Sbierski from the University of Edinburgh, and he's going to talk about the continuous and extendability of a class of three-dimensional worlds and spacetimes. We're very glad to have you.
Thank you very much for the introduction. Also, let me thank the organizers for the invitation. It's a great pleasure to be here with you to celebrate the work of Yvon Choquet-Bruhat. So I will talk today about some forthcoming work of mine about the C0 inextendability of a class of FLRW spacetimes. And I hope that this work will appear on the archive by the end of next week or so. Let me first remind you what I mean by continuous extensions, or in general like gamma extensions. So we start with a smooth Lorentz manifold Mg, and gamma is a regularity class. So for example, C0 or local Lipschitz or smooth. And the manifolds themselves, they are always smooth in this setting. And then a gamma extension of Mg is a smooth isometric embedding, J, which embeds the original manifold M into a bigger Lorentz manifold M tilde, which is of the same dimension as M, and such that the metric G tilde is now gamma regular, and also such that the embedding is not the trivial embedding, so the original spacetime has non-empty boundary in the bigger Lorentz manifold M tilde. And so if M admits a gamma extension, then M is gamma extendable, and otherwise we say that M is gamma inextendable. And so now when we look at the cosmological spacetimes, we are interested in the extensions across the Big Bang singularity. And so for this reason, let me make a definition of a past extension. And for this, let us first introduce the notion of the past boundary. So if we have a C0 extension J, then the past boundary, denoted like so, is the set of all boundary points which can be reached by a smooth time-like curve. So there exists a smooth time-like curve gamma tilde, which maps into M tilde, such that if I remove the right endpoint, then this curve maps into the original spacetime. And there in the original spacetime, it corresponds to a path-directed time-like curve. And then the right endpoint of this curve, this is exactly the boundary point B tilde. Yeah? So the path boundary is all the boundary points which can be reached by smooth time-like curves. And then a gamma extension is called a path gamma extension if the path boundary is non-empty. And if no such extension exists, then M is called path gamma inextendable. Now let me tell you about the class of spacetimes we are considering in this talk. So K is in the set -1, 0, and 1, and it parameterizes the manifolds M overline K, G overline K. So these are Riemannian manifolds of constant sectional curvature K. So these are the unique, simply connected, complete d-dimensional Riemannian manifolds of constant sectional curvature K. So for K equals 1, it's just the sphere. For K equals 0, it's Euclidean space. And for -1, it's hyperbolic space. And then we also have a scale factor, A, which is a function from the positive numbers into the positive numbers. And part of my definition of what an FLRW spacetime is that the scale factor goes to 0 when t goes to 0. Yeah? So we do have something that we want to interpret as the Big Bang singularity at t equals 0. And then this is the class of FLRW spacetimes. There are these product manifolds. Here, as I said, it's SD for k equals +1 and RD for k equals 0 and -1. And the metric is this warp product metric, as I think you're all familiar with. And you can introduce spherical normal coordinates for these maximal symmetric Riemannian spaces, and so that the metric takes this form. So where you single out an arbitrary point in the Riemannian manifold and introduce a spherical normal coordinate. And then the other differentiation of these spacetimes is whether they admit particle horizons or no particle horizon. And mathematically, this is the condition whether 1 over A, 1 over the scale factor, whether this is integrable near t equals 0. So if it's finite, then we say the spacetimes do have particle horizons, and if it's infinite, then the spacetimes do not have particle horizons. And so, as I said, so the motivation of this work is to try to understand the singularity strength of such FLRW spacetimes when t goes to 0. So as an aside, first let me mention that the results that I will be presenting, they are all for d bigger or equal than 2. So for d equals 1, of course, there's no distinction between negative or positive or vanishing constant sectional curvature. And the manifolds, they are just of this form with this metric. And in the 1 plus 1 dimensional case, you can compute the scalar curvature, and in this way see which choices of scale factor give you a C2 inextendable space-time towards the Big Bang. But as a fun fact is that all such 1 plus 1 dimensional FLRW spacetimes, they are past C0 extendable. This was also observed by past work by Galloway and Ling. And so we see that these past C0 inextendability results, they crucially rely on us having more than one spatial dimension. Okay, now let's come to the higher dimensional case, which we are also mainly interested in. So for example, for d equals 3, you can again write down scalar curvature or curvature invariance like the Kretschmann scalar, and you get these expressions. And again, you see that for a wide range of scale factors A, you can infer that you are C2 inextendable towards the Big Bang singularity at t equals 0. But one thing that I would like to draw your attention to is that, of course, the Miln spacetime also sits inside this class of FLRW spacetimes. And the Miln spacetime is where we have k equals to -1, and the scale factor is equal to t. And so we see in particular that both of these curvature invariants, that they vanish. And of course, the Miln spacetime is just part of Minkowski spacetime, so it's flat. This already shows that it's a bit subtle to infer, how strong the singularity is at t equals 0, since we also have completely regular spacetimes inside this class. And in the work I mentioned before, Galloway and Ling, they also studied these kind of spacetimes where k equals -1, and the scale factor is roughly equal to t, and they called them Miln-like spacetimes. And they gave examples of scale factors such that mg is not flat, but admits past C infinity extensions. They also gave examples of scale factors where mg is past C0 extendable, but past C2 inextendable. And they also have a theorem on the scale factor that guarantees under this condition we do have a past C0 extension. Let me tell you what this criterion is in a second. So let me first tell you what we know about the singularity strength of the FLRW spacetimes at t equals 0. So first of all, in the case where we have particle horizons, so where the integral of 1 over a was finite, the methods to study the strength of the singularity do not really depend on the sign of the curvature. And in previous work of mine, you can show that all of these spacetimes, they are past local Lipschitz inextendable. But I would not expect that this is sharp, so I would expect that you can actually prove that they're also C0 inextendable, but this is not known. And this is also true for d equals to 1. And so now the new results that I want to talk about, they are only valid for d equals d bigger or equal to 2. And they're in the case of us having no particle horizons. And so in the case of k equals +1, you don't need any other assumptions on the scale factor, and you can show that all such spacetimes that they are past C0 inextendable. Unfortunately, for the case k equals 0, which, as I understand, seems to be the most relevant for cosmology, unfortunately, there are no results available at all. And in the case k equals -1, here's first this condition which I alluded to, which was established by Galloway and Ling from a few years ago. And the condition which ensures that we have a past C0 extension is the following, that the limit of the derivative of the scale factor a goes to 1 when t goes to 0, and then that the limit of this product here exists and is between 0 and infinity. And under this condition, Galloway and Ling show that we do have a past C0 extension in the case k equals -1. And the theorem that I want to present is that if this limit here is equals to plus infinity, then the spacetime is past C0 inextendable. So in the following, I want to give you a rough outline of the proofs of these theorems. And let me first start with a fact about general FLRW spacetimes, which I will need later on for the proofs. And so we need the notion of a spacetime being future one-connected. And so let me remind you of the definition. So if we have a time-oriented Lorentz manifold Mg with at least a continuous metric, then we say that this Lorentz manifold is future one-connected if for all points P and Q, any two future-directed time-like curves from P to Q are homotopic with fixed endpoints via time-like curves. Yeah, so if you have two curves, we have two points P and Q and two curves from P to Q, two time-like curves, was a bad time-like curve, that I can find a homotopy of curves with fixed endpoints such that each transitioning curve in this homotopy is also a time-like curve. So something like this. And as something that I only want to state here as fact, since it's not really new work, but like the methods, they already appeared in previous work of mine. The statement is that if D is bigger or equal to 2, then any D plus one dimensional FLRW spacetime is future one connected. So no matter whether it has particle horizons or not. And now let me come to the outline of the proof for k equals plus 1. And this is not too difficult, it's actually quite simple, the proof. So let's do this as a warm-up. And let me remind you of the theorem. I've stated it here again. So this is our FLRW spacetime, no particle horizons. And the statement is that it's past C0 inextendable. And the way I think about these proofs is that they do not only give you like this abstract statement that a spacetime is, C0 past inextendable, but that we also learn something about the geometry, what at the level of the metric at C0 level obstructs us from having a past C0 extension. And so let me tell you how I think about the obstruction. What is the geometry that prevents us from having a C0 extension? And it's the following. So if we have a future-directed time-like and past inextendable curve, gamma, so think of this going to the Big Bang singularity at t equals 0. And the statement is that for all points S0 on this curve, there exists a T0 such that this Cauchy hypersurface of constant time t equals T0, that this is contained in the past of this point gamma S0. And then this combined with the fact that the TIFF generated, so the terminal intercomposable past set of this curve gamma, so if you look at the future of the image of gamma, that this is all of M. And these two facts together with the future one-connectedness, this is exactly what shows that we must have a C0 singularity for these spacetimes. Let me give you a brief outline of the proof of the statement. So first of all, we parameterize this curve gamma by the t-coordinate. So here is the t-coordinate, and then gamma overline, this is just a curve in SD. And since this curve is time-like, this product must be negative. And so from the form of the metric, we just compute this one here. And so we get that the length of the velocity vector of these projected curves, gamma overline, that this norm must be bounded by 1 over AS. And so vice versa, if this condition is satisfied, then this curve, gamma overline S, which is a curve in the SDs, that this lifts to a time-like curve, gamma in the Lorentz manifold. And so from this formula, the maximal Riemannian distance in the SDs, in the spaces of constant positive curvature, traveled by a time-like curve, so which starts at some time S0 and travels down to the singularity up to some time S1. Since this curve satisfies this one here, the maximal distance in the SDs is given by the integral from S1 to S0 of 1 over AS. Yeah? So here in the beginning, when I go down some time, I can travel like a small amount on the spheres, and then the light cones, they get bigger and bigger. And now I use crucially that we do not have particle horizons, so that this integral, when S1 goes to 0, that this integral is infinite. Right? So no matter how close I start to the Big Bang singularity, so no matter how small S0 is, there's always like a smaller S1 such that this integral is bigger than pi, bigger than the diameter of the spheres, right? So this shows exactly the first statement, that no matter how close I am to the Big Bang singularity, if I travel, from time S0 to S1, so there is an S1 such that this integral is bigger than pi, then the causal past of this point will contain all of the spheres. So in particular, it will contain this Cauchy hypersurface T0 cross SD, what I've drawn here. And the second statement follows, in a similar vein. Here we need to show that the future of this TIFF is equal to all of M. Okay, so how do we prove this? Okay, let's take a point in the space-time, and then an equivalent reformulation of this is that the causal past of this point will contain some points in the curve gamma, right? But now again, by the same argument, since the space-time does not have particle horizons, there's always some time S1 such that the causal past of this point here will contain all of the spheres. Yeah? And so this shows the second statement. And so you see this this kind of structure, this it doesn't really need that we have a space of positive sectional curvature. This argument only requires that we have no particle horizons and that the Cauchy hypersurface, that they are compact. Okay, so this is the obstruction. Now let me tell you why this is an obstruction. Yeah? So I mean, when you look at cosmological spacetimes, you can always somehow try to say that the volume of the Cauchy hypersurface in compact region goes to 0 or something like this. You can find geometric statements at the level of the C0 structure of the metric, but you always have to show that these statements which you talk about, that they actually form an obstruction to these C0 extensions. And so let me now show you how what I just told you, how this contradicts having C0 extensions, so why this is a singularity at the level of the C0 structure of the metric. So the proof is by contradiction, so we assume that we have a past C0 extension M tilde. And so by definition, we find a point in the past boundary, P tilde. And so what one can show is now that there exists a chart phi tilde from some small neighborhood of P tilde into this coordinate range around P tilde, such that the chart is centered at P tilde and also such that the metric is very close to the Minkowski metric. So where delta here is some small number. And so if we make delta small enough, then in particular, we can infer that the light cones of the metric are uniformly bounded. So here, this is the Lorentz metric, right? So this symbol here means that the light cones of this metric are contained in the light cones of this metric. So, or expressed in a different way, if we have a tangent vector x, which is time-like with respect to this metric, then it's also time-like with respect to this metric. And crucially, one can also show that there exists Lipschitz continuous function f, yeah, like so, which is a graphing function, so that the region above the graph of f, so this is the chart here which I've contained, this is the graph of f, the point P tilde at which the chart is centered, so that the region above the graph of f corresponds to points which lie in M, and so that all points on this graph of f correspond to past boundary points. Okay, and in this chart, we can now consider this time-like curve, which is given by this formula. So it's just the straight curve as I've drawn here, which is time-like since the metric is very close to the Minkowski metric. Okay, and here in this picture, here I use like these bounds which I have on the light cone. So here, for example, when I write G tilde W, this was exactly like this metric here, where the light cones are slightly wider than 45 degrees than the Minkowski light cones, and I know that the light cones of this metric must be contained in the light cones of this metric. So this gives us causality bounds on the causal diamonds, for example, in the extension. Okay, so here we now make epsilon 1, which was the spatial extent here of this chart. We now make epsilon 1 slightly smaller, so that if you look here at the point gamma tilde of epsilon naught over 2, so that the future of this point, and here the green light cone is the light cone where all vectors in this light cone and all straight lines, they have to be time-like curves with respect to gamma tilde. So this is the set, which is the light cone, which is contained in G tilde. So that in the future of this point contains like a small time slab here in this chart. So it contains the set. And then we choose S naught, here parameter on this curve, small enough such that this causal diamond here is compactly contained in the chart, in U tilde, so the way I've drawn it. And now we look at the time-like curve, which corresponds to gamma tilde in M. And now I claim that the future one-connectedness, which I've told you about before, implies the statement. Okay, so let's go through this. Here the first statement, so here we have the time-like diamond, so the future of P tilde intersected with the past of gamma S naught. And so here I write this just as the futures of the gamma S's, where S is strictly bigger than 0, so where I don't include the point P tilde. And so this is something you probably are familiar with. So this holds in general for if you have a smooth Lorentzian metric. It also holds if the Lorentzian metric is only continuous, if the curve leaves smoothly at P tilde. So this is something we need to use here. But let me not go into this detail. So this just expresses this time-like diamond in this form.
This is the future one-connectedness.
Yeah, so this was what I've told you here about. So that if you have any 2 points P and Q, where Q is in the future of P, that any 2 future-directed time-like curves from P to Q, so here gamma 1 and gamma 2, that they are homotopic with fixed endpoints via time-like curves. And so the non-trivial part is now this part here. Since this is causality with respect to the small chart U tilde, so it's all the points which lie in the future of P tilde and the past of S, of gamma tilde S naught, with respect to this chart U tilde. And now I claim that this corresponds to exactly the same set, the futures of the gamma S intersected with the past of gamma S naught, but now with respect to the causality of M. So this is the non-trivial part. And so one inclusion is, again, trivial. So if we have like a point in this set, then we can connect it by a time-like curve, say from here up to here. And since the region above the graph of F is contained in the original spacetime, this is also a time-like curve in M. Yeah? So this set here is trivially contained in this set. But the other inclusion is non-trivial, since what could happen is that you have like a path-directed curve of starting at gamma S and M, which leaves this chart, then enters it again and goes to P tilde. And this is something to get the other inclusion. Here we need the future one-connectedness. Since if you have the point here in M from gamma S and gamma S naught in M. And so you want to show that a point in this set is contained in this set. Okay, take a point in the set, you connect it by a future-directed, you choose a future-directed time-like curve such that this point lies on it. And now by the future one-connectedness, we know that this curve can be homotoped exactly to this curve here. And now you can see that since these causal diamonds are compact, if you write down a homotopy via time-like curves, this homotopy has to stay with, inside this, this compact causal diamond. And this exactly gives you the other inclusion. Okay, and now by the abstraction which we have shown before, I know that this TIFF here is all of M. So this set equals the past of the point gamma S naught. And by the abstraction, this contains like a compact Cauchy hypersurface for T naught small enough. And so this, now you see, already looks quite dodgy that inside this causal diamond, we know that there must be a Cauchy hypersurface, a compact Cauchy hypersurface completely contained inside the set. And there are many ways how you can contradict this. So one is, for example, that you just take a time-like curve which does not intersect this, causal diamond here. And now this is a time-like curve which starts to the future of the compact Cauchy hypersurface T equals T naught. Is past and extendable, but does not intersect this causal diamond where the Cauchy hypersurface T equals T naught is contained in. And so this is a contradiction to the global hyperbolicity of this. So this shows how to show that, you know, what I've told you as an obstruction is an obstruction to continuous extension. Okay, so this was the warm-up. The case now for k equals -1 is slightly more complicated. So I have roughly 20 more minutes, 25 more minutes? No? 25 minutes, good. So let me remind you of the theorem that we want to prove. So we again need more than two dimensions, more than two space-time dimensions. This is our manifold with this metric, where this is the hyperbolic metric of constant sectional curvature equal to -1. We have no particle horizons, and we need this additional assumption that this product goes to infinity. So we will see in a second how this crops up. And then the statement, under these conditions, the spacetime is past C0 and extendable. So I need to establish a few properties of these FLRW spacetimes. The first one is the following: that if I have any such FLRW spacetime without particle horizons, then if I take 2 points R and S, where R is in the past of S, then I have the following property, that no path-directed null geodesic emanating from S intersects any path-directed null geodesic emanating from R. So I hope this is intuitive, perhaps also from the picture. I mean, it's the same, for example, in Minkowski spacetime. If you have one point and another point in the past, that, you know, the light cone of the point in the past is completely contained in the light cone of the point in the future, and that's the same for these FLRW space. Let me not go into much detail of this. And this slide looks a bit intimidating, so let me first draw a picture. So this slide characterizes the terminal indecomposable path sets of this class of FLRW spacetimes. And it's perhaps easiest to see what is going on by the explicit example of the Miln spacetime, since there we do have a smooth extension. And recall that the Miln spacetime, so where we have k equals -1 and a of t is equal to t, that the Miln spacetime just embeds into the time-like future of the point 0 in the d+1 dimensional Minkowski spacetime. Right, and the slices of constant t, these are these hyperboloids. And what I want to do now is I want to characterize the TIFs. So let's say we take here this time-like geodesic and introduce these spherical normal coordinates centered at the point p hat in my hyperboloid. Then I get these, sorry, about switching between slides and board. Introducing these spherical normal coordinates, the metric takes this form. And then I introduce a new function tau and u, where u here is now a null function, iconal function. And in the case of the Miln spacetime, the sets of constant u, these are just the cones, like so, where in this direction we have u goes to minus infinity. And the level sets of constant r, these are exactly like these cones of smaller opening angle, and r goes to infinity when these cones approach the light cone. And so we are now interested in, given this coordinate system which we have, how can we characterize the TIFs of these coordinate system, the TIFs of the spacetime with respect to these coordinates? So what I mean is, if we take an arbitrary time-like curve like this, how can we characterize the TIFs? And the first statement of this proposition is that if we have an arbitrary future-acted and past and extendable time-like curve, so a curve which goes here to the singularity, or in this case, the light cone at t equals 0, then we must either have that the u coordinate goes to minus infinity. So this would correspond to the curve going to the vertex here in Minkowski spacetime, to the vertex of the light cone. Or the u coordinate must go to a finite value. This is this case here, where it approaches the light cone. And in this case, r goes to infinity. This is what I've just drawn here for you, right? These cones, they have to open up wider and wider, so r goes to infinity. And also by omega, I mean the projection of this curve onto the SD minus ones. Omega must have a limiting point on the spheres. Yeah? So somehow, in some sense, think of it as, some form of past null infinity, where each point here on past null infinity is labeled by a u value, and then if u is not equals to minus infinity, also by an angular value on the spheres. So this is the first statement, that if we have a future-acted and past and extendable time-like curve, either u has to go to minus infinity or u has to have a finite value, and in which case the projection on the spheres has a limit. And in the first case, if u goes to minus infinity, then the TIF is again all of m. Yeah? So this is, I guess, obvious here from the case in the Miln spacetime. And then the next statement which we need is that if we have two future-acted and past and extendable time-like curves, which do not go to this vertex, so where u for both curves has a finite value, and so then by 2 also the angular projections have a finite value, then if they have the same value, then the TIFs are the same. So this is, the first step in, labeling the TIFs by these coordinates. And the second statement is, if the limits of the angular projections are the same, and u1 is less than u2, then the TIF of gamma 2 is contained in the TIF of gamma 1. Yeah? So this is just the statement here, that if I have these two curves here, where u1 here is less than u2, that the TIF, the future of this curve, contains the future of this curve. Okay, so now let me tell you what the abstraction is for C0 extension. And this is now where we need the additional assumption which be made up here. Okay, so we again consider spherical normal coordinates centered at some arbitrary point in the hyperboloids, and we label by sigma t naught the surfaces of constant t, the Cauchy hypersurfaces. And then let gamma I be two future-directed and past inextendable time-like curves parameterized by the time coordinate t, such that these curves, they do not go to u equals minus infinity, and so that they both have limiting values on the spheres, which are not the same. This is important here, which are not the same. And so we take also a point q in M, such that these curves, they are not contained in the past of q. Yeah? So for example, here, the setting q would be somewhere here, say. Yeah? This is here, the past of qm. So the two curves are not contained in the past of q. And then the statement is that in the Cauchy hypersurface sigma t naught, if you exclude the past of this point q, then the distance of these, of the intersection of gamma 1 with the hypersurface t equals t naught and gamma 2 intersected with the hypersurface t naught, that this distance goes to infinity when t goes to t equals 0. And the way you should think about this is that this condition here, which Galloway and Ling, where they needed a finite limit to have a C0 extension, that this exactly gives us that these limiting spheres here on the light cone, that these limiting spheres, that they have infinite radius. Yeah? This is how you should think about this. Let's see how this goes. So first of all, so to prove this abstraction, okay, here's our arbitrary point q. And since we have no particle horizons, I know that the past light cone of q will in particular intersect the geodesic of constant p bar. So this light cone will intersect the t-axis of the coordinate system, which is set up like this.
So you're assuming that the metric is smooth in the space-time, right? It's only at the boundary that.
Yeah, so the FLRW spacetimes are smooth.
You don't, so let's say it should be C2. But you don't, probably you can even do with less, but C2 is certain. Yeah, probably that would be fine. Yeah, so here, since we have no particle horizons, the past light cone of Q will in particular contain a point P, which is of the form TP and then P overline. And so the causal past of this point P is contained in the causal past of Q. And so in particular, sigma T naught without the past of Q is contained in sigma T without the causal past of P. Yeah? So this here is a bigger set. So this is causal past T equals T naught without the causal past of P. And this is contained, is bigger than if I only exclude the causal past of Q. And this set here, since this is where we have centered our spherical normal coordinates, the causal past of P, it's a set which only depends on R in these normal coordinates, and it's just given by R bigger than the maximal space-like distance that can be traveled by causal curves, which is again given by the integral of T naught to Tp over 1 over AT dt. And now since, so recall we want to show that this goes to infinity, but now sigma T naught without J minus PM, this is actually bigger than this set, so it suffices that this goes to infinity since, we allow for more curves to get the distance down, to get it lower. But now since, this is the metric on these hypersurface of constant T naught, but now since R is bigger than this integral, if I put this, the metric is strictly bigger than this metric. And now the hyperbolic sine function grows like the exponential, right? And so by our assumption is that this product here, so the factor appearing in front of the spherical metric, that this goes to infinity when t naught goes to 0, right? This is our assumption. And this is basically what proves the obstruction, since if we have these two curves, gamma I, which have different limiting points on the sphere, so here where omega 1 is not equal to omega 2, then the spherical distance in the SDs, SD minus 1s, has to be bigger than, say, epsilon, right? And so if you want to connect these points now, and by the orthogonal form of the metric, okay, you might need to travel some distance in R, but this just makes it bigger. So we have to transverse this epsilon distance in the spheres SD minus 1, but since the factor goes to infinity, the distance goes to infinity. And this is what I told you before, that you should think of these spheres at null infinity having infinite radius. Okay, so now let me show you how to show again that this is indeed an obstruction, so that you can't have a C0 extension in this case. Again, assume that we do have a past C0 extension. And now I crucially use, again, that the dimension, space-time dimension is at least 3. So we have here the same setup that we can find like these charts where the metric is close to the Minkowski metric. I have bounds on the light cones, and I have this graphing function. And so recall that the graphing function was local Lipschitz continuous. So in particular, it's differentiable almost everywhere, right, by Rademacher's theorem. So I can take one point on the graph of f where the graphing function is differentiable. And now, since I am in at least 3 space-time dimensions, even if the boundary is null, it will contain at least one space-like direction. Right? And this is what I use in order to set up these coordinates. I take a past boundary point p tilde, where the graphing function is differentiable, and such that the derivative in the first coordinate direction is equal to 0, so that it contains d by d1 as a tangent vector, which is space-like. Yeah? So this is what I've drawn here. So the one space-like direction goes in this direction, and the other coordinates go into the screen. Okay, and now since the derivative in the first coordinate direction vanishes here at this point, there exists a small value of mu, such that the graphing function is contained in this small cone with opening angle 1 over 10, yeah, small region. So this gives me like a quantitative bound on the space-likeness of this boundary in the x1 direction.
How this direction is found where the gradient of f finishes?
So I work in at least 3 space-time dimensions, and so I get this Lipschitz continuous graphing function, and so in particular I know I can find a point where this graphing function is differentiable, so where this Lipschitz graph has a tangent space. And so of course you can show that the tangent space has to be either space-like or null, but you don't actually need this. I mean, you know that the tangent space is at least 2-dimensional, so it has to contain at least one space-like vector, right? And then you can, once you have the space-like vector, you do a coordinate transformation to put the space-like vector into the one direction, d by dx one direction. Okay, and now here comes the slightly complicated setup, and this will explain what we, in a second on the next slide, what I've shown you before, like the obstruction and the proposition and so. So using the setup, using the space-likeness of the boundary, first of all, I mean, here we don't use the space-likeness of the boundary. Here we just choose, again, 2 points S tilde and T tilde, so that the causal diamond of S tilde and T tilde is compactly contained in the chart. Okay, no big deal here. And then we choose 2 points R tilde and Q tilde. The first one, R tilde, lies on this cone which bounds the graph of f. And since it lies on the cone, it in particular lies in the image of M, of our original spacetime. And the other point, Q tilde, we choose to lie on the graph of F. And I also want that these 2 points, Q tilde and R tilde, that they lie in the time-like past of S tilde. So here with green, I have again denoted like the light cones, which are certainly contained in the light cones of our metric G tilde. And in red, I have denoted the upper bound on the light cones. So every vector or every straight line has to be, the causal curves of the metric G tilde have to lie inside the red light cones, yeah? While the green light cones, they are certainly time-like with respect to the metric G tilde. Yeah, so the points R tilde and Q tilde, they lie in the past of S tilde. And then I consider also these 2 straight time-like curves, which lie in the x0, x1 plane, gamma tilde 1, which goes from S tilde to P tilde, and gamma 2, which goes from S tilde to Q tilde. And they correspond to M, to future-reacted past and extendable time-like curves, so they go to the past singularity at t equals 0. So now we want to look at the causal diamond here from between P tilde and S tilde and Q tilde and S tilde. So perhaps let me draw this picture here again on the board. So here we have P tilde, here we have Q tilde, here we have R tilde, S tilde, and I'm interested in this time-like diamond and this time-like diamond. Yeah? These are the 2 sets I've written down here. And as before, you know, using the trick with the future one-connectedness, you can show that these time-like diamonds in the set U tilde, that they correspond to these time-like diamonds with respect to the causality of M. Yeah? This was the same trick as before using the future one-connectedness. And so what we want to do now with the setup is that we want to relate the setup to the geometry of M, right? So we have like these 2 inextendable, past and extendable time-like curves in M. And I want to know, you know, to which points of, you know, past null infinity do they have to go? And from the picture here, it is clear that neither this past time-like that neither this time-like diamond is contained in this time-like diamond, nor the other way around, right? Since the boundary here is roughly space-like, so this time-like diamond will not contain points which lie, you know, just above P tilde, and this time-like diamond will not contain points which lie just above Q tilde. So neither of these sets is contained in the other. But now, from the proposition we had before, right, we know that if the curve, for example, goes to u equals minus infinity, then the TIF is all of M. Yeah? So, but this cannot be, right? Since if the TIF was all of M, then, you know, say the TIF of gamma 1 was all of M, then this set should contain this set, or the other way around. Yeah? So from this, we can infer that these 2 curves, gamma 1 and gamma 2, that they have to approach finite values of u. And now, again, with the characterization we had before, if the 2 curves approach the same omega value, so the point on the sphere and the same u value, then the TIFs would be equal. But again, you know, this is something we can rule out since they are clearly not equal. And also, if they have the same angular direction but different u values, then one would be contained in the other. So this also cannot be. So from this characterization we had before on the TIFs, we infer that these 2 curves, which I have constructed here in the extension gamma 1 and gamma 2, that, you know, in the original space-time, they must have a finite limiting u value, and they must also have limiting values on the spheres, which can't be equal. And this exactly, puts us in the context to use the obstruction. So, to finish the proof, I think I'm nearly out of time. Let me, for the time being, assume the following claim. The claim is that if I look at the causal diamond, the future of T tilde intersected with the past of S tilde, and I exclude the causal past of R tilde, that this set is not entered by path-directed causal curves starting at R in M. And so using this claim, so this should be an R tilde here, if we denote R by the point which corresponds to R tilde in M, using this claim, we see that these two curves, gamma 1 and gamma 2, that they do not lie in the causal path of R in M. And so then we can characterize these two curves by the time coordinate, and using the obstruction, we exactly infer that the distance of these, if we look at a hypersurface of constant t, which intersect these surfaces, that the distance of these points in the hypersurface t equals t naught. If I exclude the causal path of R, that the distance here has to go to infinity. But now, using this setup, this is something I can contradict, since these surfaces of constant t, when t goes to 0, they have to approach the graph of f. And so in particular, I can connect these 2 points here on the curve gamma 1 tilde and gamma 2 tilde just by a small smooth curve, which I've drawn here, contained in sigma t naught. And using the uniform bounds on the metric, and that this is a finite curve, I can show that you can connect these 2 points by a curve of finite distance. And this is, of course, in contradiction to this statement. And here the crucial point is that, this curve here, which connects these 2 points, that this is not contained in J minus Rm, in the causal path of R. And this is established exactly by this claim. So perhaps in the last minute or so, let me again tell you what this claim means. Yeah? So here we have this causal diamond, which is contained by the red dashed lines. And from this set, I exclude the causal path of R tilde in U tilde. So here, this set. And I say that no other point in the set comes from a point which lies in the causal path of R in M. So how could this happen? So recall that this is, as I've drawn it, it has at least 3 spacetime dimensions. So what could happen is that you look at a causal path-directed causal curve starting at R in M, and then it leaves this chart and then enters the chart again to reach a point in here, something like this. Yeah? And so this claim says that this is not possible. And so on the last slide, let me tell you how one shows that this is not possible. So here I've drawn the scenario. If this claim were not true, then there would be like a causal path-directed curve in M, which starts at R, leaves this chart, enters the chart again, and reaches a point Z tilde, which lies in the region bounded by the red dashed lines, which is not in the causal path of R tilde with respect to U tilde. But now, since Z tilde lies in the causal path of S tilde, in particular, it has to cross the light cone of the past light cone of S tilde in U tilde. Now, the past light cone of S tilde and U tilde is generated by path-directed null GD6, right? So in particular, this curve has to intersect a path-directed null GD6 emanating from S tilde. Okay, this is the null GD6, which I've drawn here. Now, this null GD6 connects S, which lies in the future of R. So in particular, it does not lie in the past of R, with a point which lies in the causal past of R. This nullity sig, in particular, must cross the boundary of the causal past of R, which is again generated by path-directed nullity sigs emanating from R. In particular, here along this nullity sig, there must be a point, as I said, which lies in this set in the boundary of the causal past of R, in particular, where there exists a path-directed nullity sig from R to this point. Yeah? And this is exactly the proposition which we had before, that there are no, or in contradiction to the proposition we had before, that there are no path-directed nullity sigs emanating from R and S which intersect. And so this exactly establishes this claim and finishes the proof. Thank you very much.